keep on my lap. Pick them out though. He gets picked up. And we have an extra seat. I mean, we could do one.
No, 98. It probably doesn't matter. 98.
Really? Yeah. 90? How does that feel? Really, 3 donuts sandwich. I don't like 3 donuts. Like, no, like, take things like, Bessy's first language, I have a hard time understanding. It's multiple choice.
Okay, oops. Okay, so let's start. So I just want to remind you that Quiz 2 is on Monday, and it covers the material from the last quiz to the end of DNS. So that would have been the end of last class. Okay? And if you look on Piazza, I actually have the learning outcomes broken down by the quiz. So you'll go and says, okay, here's quiz 2, and then it lists everything, and then it says, okay, here's where the stuff for quiz 3 would start. Okay? So you can go there and you can see exactly where it is that you need to be looking for. And then there are the practice questions and stuff like that. Okay? So before I'm going to ask for questions in a moment, but there's one thing that I wanted to clarify, because I made an error on Wednesday. So on Monday, on Wednesday I showed this slide, and I said 199.783.42 was in AS1 on the one hand and AS4 on the other. And so I never thought too much of it when I did this, and then I was reading something and I said, I wonder if they actually are in different ASs or not, or whether they're actually in the same AS. Well, it turns out they actually are in the same AS. So even though these machines are distributed in different parts of the world, so we had the example where that particular address was in Vancouver and another one was someplace close to Zurich, they would be announced, as far as BGP is concerned, they would be seen as coming from the same AS. So when the one on the right-hand side announces to AS3, it says, okay, AS20144, that's who you're connected to, and so is AS2. Okay? So now, just to sort of put some perspective on this, okay, so we sort of look at this and we say, okay, there's what I showed you. I said, okay, it's going to announce a routing cost of 2, for example, from AS3 to AS2 to get to 199 and similar sorts of things. But now what you need to sort of do to try and convince yourself that this will work is say, well, what if it looked like that? Okay? What if the real sort of physical connections were like what I've drawn there now? I think, given what we talked about earlier, that everyone should say, yeah, that's okay. It's okay to have cycles and everything like that. And you'll notice that as far as AS2 and AS3 are concerned, that picture and that picture are indistinguishable. It gets exactly the same information as far as BGP is concerned. It would say, what is the AS that it's in, everything like that. The two of them will look exactly the same. And so those two, as far as AS2 and AS3 are concerned, are in fact identical. So there's nothing that stops you from having your AS in some sense physically split up. And I mean, if you really sort of wanted to say, well, how, if you're really uncomfortable with that picture, right, you could say, well, that's the picture that it really is. And as we saw, ASs are just these organizational things. There's nothing to say that an AS can't span the globe. right? It just has to be owned by one particular organization and have a way for them to sort of interconnect things, roughly speaking. Well, they don't even have to be interconnected. So they just have to, you could do something like that. Okay? Any questions about that? Yep.
So this means that if you have any ASs that have these types of IPs that can be put in multiple locations, that they have to have all of the same IPs across every AS. So you have.
I think that's the case. And the thing that I was going to do before coming to class but didn't to sort of verify that was you can actually, so that AS there, AS20144, is in fact the proper AS for 199.783.42. Okay, so I actually looked that part up. So that is in fact true. And then what I was going to do, but I kind of got sidetracked and forgot to do, there's, if you go to Hurricane Electric, there's a little part of the website there you can go to and you can sort of say, okay, here's an AS number, what IP addresses do they have? And so we could see whether or not, presumably they were all, they'd all announced the same thing, but the thing that I was curious about was whether or not AS20144 has exactly one node in it, and that's the node that belongs to the root name server. And then what that would be kind of, because then what you could have is, then you don't have a lot of conflicts, right? Then you don't have to worry about the issue that you said, like they have, well, they would in fact be the case that you said. The AS would have exactly the same set of IP addresses. They'd have exactly one. It would be that one. And as we also sort of mentioned, when you have multiple machines like that, although they're in, so essentially what you have is you have this one machine. You have one interface going out here. That would be the 199.783.42 interface. And then we have to have a typically you have another interface into it that has some other IP address. And this is the one that you distribute the updates to. So this is how you'd say, okay, this is where, if this is a root name server, this is where you would be saying, okay, the .ca name servers have changed their addresses, or there's a new top-level domain, a generic top-level domain or something like that that's being added, and so you want to update that information in there. So you have these sort of secondary access points. And so this guy here would be in AS20144, possibly in multiple locations, whereas this one here would be some other IP address that in fact would be machine unique. And I'm going to use the term machine unique to mean that there's no other machine on the internet that has that IP address associated with its interfaces. Okay. So any questions or comments about that? So I know that, oh, sorry, just a sec. I know that there were a few people after class that were asking some questions about that, so hopefully this will help clarify things a little bit.
So 199, that one, 199.783.42, that's a root name server.
Yeah.
And the machine that's unique connecting to it is a mirror of that, or?
No, you mean this one here?
Yeah.
No, that's just, okay, so, excuse me. Often with pieces of equipment like this, you have two interfaces. So you have one interface that is the interface that the world sort of sees and wants to work with for routing purposes and stuff like that. And then you have another interface that the world can see it and everything like that, but it's not really meant to do anything other than for you to connect to it and to do your updates to, in this particular case, it's not the routing tables, but it's the mappings for the DNS tables. Okay, so it's just, and that's, you know, that would be no different than your laptop or whatever having a wired and a wireless type connection. So, except that one is sort of the public view, that's AS20144, and the other one is sort of not meant for anyone to really use except the people who want to update it.
So follow-up is, you use 199 to get to the root server, to have it do its root server.
So this is the address that everybody in the world who wants to contact the root name server would use. Yeah.
Right. But if you use the machine unique whatever IP, you connect it, but you don't get the same access or the same.
That's right. So in fact, they probably wouldn't even answer DNS queries there, right? It would probably be some sort of I don't know what it would be, but you could imagine it might be SSH, and you have to go through an authentication procedure to log in, and then you have to type commands and stuff like that.
Different doors to the same.
It's a different stores to the same machine. Yeah. Yeah. Yep.
So the other thing is saying, you're saying that this is belonging at different AS.
Yeah, this one here, yeah. Yeah. So this would be the one that if we knew what this address was, right, and if we looked it up in Zurich, or sorry, we looked up that IP address, we'd find it at one location in the world, probably near Zurich, and then the one in Vancouver would be different, and we looked that one up, and it would be near Vancouver. Okay. So sometimes this is also called Anycast. So if you look up this, if you look this up under the, if you like Google Anycast, you'll also get a fairly good description of what this is. Okay, so any question? Oh, no, that was identifying someone who was going to go sit down. Any questions then? Okay. All right, so today then what I want to talk about is what primarily performance. Okay, and so we're going to, in particular, we're going to look at this notion of performance metrics. And I'll explain a little bit what I mean about that in a moment. But the idea here is we're going to talk a little bit about the internet first. And then basically what we'll say is, well, there's lots of things in the internet. Are there some metrics or measurements or things like that we can apply to all of these different components? So that from a perspective from outside, you really don't care whether it's a router or whatever it happens to be. You actually are more interested in how it contributes to these various metrics and what happens. Okay, so today should be the case that you should be able to identify some of the major components of the internet, classify them in various ways by function. We'll look at the terms bandwidth, throughput, output, bandwidth, throughput, goodput, and delay, and we'll also talk about jitter. And we'll be able to do some calculations with that sort of stuff. So what we're essentially doing now is we're making a little bit of a transition. So what we've been looking at so far is some of the stuff that puts it together. So we've looked at DNS, DHCP, some of those types of applications. And now what we're going to do is we're going to say, okay, let's look at, for example, not right away, but in a few lectures, how does TCP work? How does TCP actually change? What we know so far is that the network is unreliable, that if we put some data onto the network, that we chop that data up and we put it into packets. We know that those packets may arrive out of order, that the amount of time it takes for a packet to get from one location to another could vary. The packets could get lost. The packets might be of different size. So, and yet we use things like, when you do SSH and stuff like that, you don't see characters disappear and those sorts of things. They always show up. So how do we do that? How do we turn this unreliable substructure into something that's reliable? Okay, so that's what we're sort of looking at. And to do that, the first thing we want to do is we want to understand a little bit about what the underlying performance characteristics of our network, because it turns out that knowing something about how the network performs and what it does contributes to how you do these other things. Okay, so that's why we're headed in that where we're headed. Okay, so why don't you just take a moment or so, maybe just write down, and I'll ask you to contribute. Okay, think of everything that you can, or that might make up a part of a network. Okay, so okay, I've got this computer network. I have my machines here. I'm going to talk to a machine someplace else. What are all of the? If I were to go out and put together a network, in some sense, what would I have to buy? That's another way of looking at it. What are all of the different things I might have to buy to build a network? Okay. And so just think about that for a moment. I'm going to erase the board here, and then we'll come back and take your ideas on what you might need.
So I think, yeah, for that, because this is I guess. Oh, any code like this.
Okay, so now that you've thought about that for a moment, so how about some suggestions on the type of stuff that we might want to buy or need to put a network together?
So first, transmission medium, so it could be wireless or wired.
Okay, so we need to buy some wire.
A router.
Okay, one person at a time. Okay. Okay, so we got a wire.
If your router is big enough for your line cards and cards.
Okay, so is that enough? That's it?
Transceivers.
Okay.
Computers.
Computers, okay, that's good. We'll need some of those.
Switches.
Switches, okay.
Network cards or NICs.
Okay.
Servers.
Servers, okay.
We need to have some central hub for translating and
Sorry,
IPs.
Sorry, I missed.
DNS server.
Okay, so we need some more. Okay, so I think what you actually identified was something slightly different. The way you said it was software. Would that be a good, to provide services on computers? Sure. Okay. Software.
License. Builds a network.
License, okay, well, we'll sort of skip that part. Yeah. But we'll probably have to license things, yep.
What about networks where things are like satellite communication? That count?
So we might have to buy, for lack of pardon, yeah, okay, sure. Antennas, which I can never spell. Maybe even a satellite. So, anything else? Well, what about, we could actually, under this, we could actually add fiber. So, although there's sort of copper wire-based thing, there's fiber, we have notions of antennas, so that would be wireless type stuff. We have routers and switches, there's also things we can call hubs. Okay. And then we have this class of things here, line cards, transceivers, NICs, and stuff like that. We have computers and servers, we have some software. So roughly speaking, that's essentially what you need to put together a network. And we can then, I put those in columns because we can sort of classify those things by, well, what do they do? In a broad sense, okay? So in this part here, we might call these hosts. And in addition to computers and servers, you also sort of need clients. So by that, I'd be meaning things like, your laptops, cell phones. So those particular things isn't so much that you're buying those ones because you're typically sort of providing the service for them. But they're the kind of the things that you need. I mean, if you didn't have those, you wouldn't be building a network, right? So they're kind of like, okay, we need some of those sorts of things. And then, of course, we need the software to run on all of this. So we have things like hosts. And then we have stuff here that's essentially the communications medium. How do you actually carry the signal? So this is sort of for carrying the signal. Right, and so we'll need, if we have wires and antennas and stuff like that. Actually, I should have actually put antennas over here. Maybe not. They're passive. That's go back here. Okay. So, but these things here, they're responsible for carrying the signal somehow. Right? We have these sorts of things here, which are actually responsible for moving the signal from one spot to another. By moving it, I mean that when we go through a router or a switch, we actually sort of change the direction of what the signal is doing in some sense. That's a strange sort of metaphor. But the signal comes in, and then we say, okay, we don't want it to go there anymore. We want it to go over here. Right? So we're essentially somehow switching the signal. And then when we combine switches and hubs and routers and things like that with line cards and transceivers and NICs, right, what we can do is we can cause the signal to change from one carrying media, so wires, fiber, satellite, or whatever, to another. So these guys here, if you're not familiar with what line cards and transceivers and NICs and stuff like that are for, or what they do, their job is to take a signal, or well, sorry, depends upon where you want to start with this. Okay, if you start from the computer side, they're essentially told, they're given some data, and they said, I want you to send this data, convert it into however it is that you signal for that. So in the case of wireless, it would be, whatever they do to make radio waves. Okay? If it's the case of fiber optics, it would be, okay, turn this thing into pulses of light. If it's wire, it's turn this into whatever electrical signals look like on a wire. Okay, so clearly you can tell that I'm not a hardware person, but essentially that's what all of these sorts of things do, is they take the digital information that we have and convert it into some way that we can then propagate it. And then what we have to do is we have to propagate it over one of these types of media, relative to whatever that. So these things and these things go together. And then when the signal shows up at the other end, it does the reverse. It takes the signal and converts it into digital data for us. So we've got those sorts of things. And then if it happens to be that we hit a router or a switch, well, it can change it from, for example, we might change it from a fiber signal to a wired signal or to a wireless signal, anything like that. So that's sort of what these guys do. They sort of are the switching fabric, or they're the ones that somehow change the signals for us without interpreting them or anything. Okay, just a sec here, the battery's going down. Okay. Now, to remember where I was, that should have got myself. So we've got these signals, so they come in, we move them around, and then we have, the routers and switches, they change the directions of things for us. And then the computers and servers and clients are essentially the stuff that consumes it or produces the signal. Okay. So all of those things go into making a network. And so there's sort of a picture of it. Right? So we've got moving data from one location to another wire. That's basically the things that I've talked about on the board. So they're just there. We've got their hosts. We've got these notions of end systems. So those are all of the things that we go into the network. Okay? So if I draw a picture, right, then you can watch my very poor animation. For some reason, the particular paths don't line up anymore from the slides that I had before. So we sort of send packets through all of these sorts of things. And they might go from, so for example, when we start on the top left, right, it starts out wireless, might then go to something that's running on fiber, might end up going on something that's running on wire at the very end. Right? And then we could have things like firewalls and stuff like that in there that are essentially, in this category, routers, switches, hubs. They kind of determine how the signal is going to propagate or not. And, whoops, some more of those going through there. Okay. So now that we have a little bit of a picture of things, the next thing I want, so it's going to seem disjointed because now I'm going to ask you, now let's just forget, let's not pay attention to everything that I just talked about, okay? So the next step is to say, okay, let's turn our brains off with respect to that for a moment, and we'll come back to this in a bit. But first, let's talk about some terminology. And what the goal of this terminology is to say it actually turns out that as far as our protocols are concerned, think about where our protocols run. If we look at network protocols or the transport level protocols, all of those things run on computers, or in some cases routers. But essentially what they're doing is they're taking data and they're processing it. They're not processing signals. Much of this stuff here is associated with the processing of signals and the moving of signals around. And the stuff that we're kind of interested in this course is more, let's look at the data. Okay? So from the perspective then of our course, it doesn't kind of matter whether it's a wire or fiber or switches or hubs or what the line cards are and stuff like that. We can actually characterize our network from a different perspective. And that's what I want to, that's more important to us as far as data is concerned. So this is what makes, that's physically what it makes it up. But for the most part, we don't care. There are other things that we care about instead. And so that's sort of the next part that says, yeah, all of this sort of stuff here makes up the network, but there are other things that we care about. And what's kind of interesting about these things is how they affect this other stuff. Okay? And so that's sort of the next thing is, okay, so what's some of this other stuff? Okay? So, whoops. There. Okay, so let's, if you've got your laptop or something like that out, what I'd like you to do is something like, if you're on Windows, it's ping -n, or if it's on a Linux or a Mac, you can do ping -c, and then what the second number is a count. So what I want you to do is I want you to pick some host, and ping it for that number of times, okay? And then once you've sort of done that, let's just sort of look at the numbers for a moment, and then we'll talk and see, well, what do those numbers tell us? Okay. And okay, so what I'm going to do is I'll sort of, you can continue to sort of do this in the background, but I'm going to ping www.ubc.ca. Okay. I've never seen the emergency part show up there before, so I'm not sure what that means. Okay. So now let's look at so first of all, look at the numbers in the right-hand column. So what the number in the right-hand column is doing is it's saying, so when you do a ping, what happens is it sends this little packet out, it goes to the host, and if the host is willing, it will essentially just turn around and send it back to you. Okay, so that it's sort of like saying it gets its name from those old war movies and stuff like that, where you have sonar, right, and they send a little ping out, and if there's another submarine or a ship out there, that you get that echo back. So that's sort of that's why it's named that. Okay. And then the amount of time on the right-hand side. Okay. First of all, what do you notice about it? So I'm pinging the same host all the time, right? So unlike in the war movies and stuff like that, when they do a ping, right, they measure how long it takes for the signal to go there and how long it takes to come back, and then knowing how quickly sound moves through water or making an estimate of it, they have a guess as to how far away that object is. In this particular case, I'm going to presume that whatever www.emergency.ubc.ca is that, in fact, it's at a fixed location. It's not busy wandering around, and that, as a result, it's the same distance from me all the time. So it can't be the case, then, that the number on the right-hand side is, in fact, some measure of distance for this particular example. Okay. So the number on the right, and you'll notice down on the very bottom here, so I should back up a little bit. So what that time is, in fact, is just like an echo time in the movies, where they start a timer, they send the packet out, they hear the echo, and they just say, okay, how long is that? Okay? So that amount of time, they call that a round trip time. And then on the bottom line there, it goes, what was the minimum amount of time it took to reach that destination? Because remember, in our case, it's not some wild destination that's presumably wandering around. It's fixed in a particular location. And even if you were wandering around, that would almost mean you were using wireless, or have to mean you were using wireless. And if you're using wireless, well, I believe those signals propagate at the speed of light. So you're wandering around in a classroom or something like that wouldn't affect some little pings. Okay, so we've got the minimum amount of time, the average amount of time it took, the maximum amount of time it took, and then some measurement of deviation from the average. Okay. So from this, we see that the least amount of time it took was about 3/4 of a second, right? And at the most that it took, not a second, of a millisecond. That would be a long time if it was 3/4 of a second. 3/4 of a millisecond. Average time is about a little over 1.5 or 1.6 milliseconds, and the most amount of time was 12 milliseconds. Okay. So this amount of time that it takes to get an answer and back, okay, that's referred to as latency. So what's the latency of this? It's also in this case referred to as round trip time, but that's not the number. That's not the thing that I want to be talking about here. I want to be talking about latency. So the notion of latency is you send a signal, and how long does it take until you get a result in some way? And then you can define the result in a number of different ways. So let me just, if I do this right. Whoops. I'm going to skip ahead a moment. Okay. So, okay. Oops, that's not it. I skipped way ahead is what happened. I skipped right to the very end. Now I have to find out where I am. Okay. So this variation that we're seeing, okay, so first of all, a measurement of time from when we send it till we get an answer back. In this particular case, because we're going someplace and we're getting an echo, it has two names. It's got a round trip time. But another way to look at that is to say, well, what's the latency for getting that answer? How long did it take to get that answer? So this is a common term that's used in networking, is latency. So it's the delay from when something is sent until it is received. And this is always the tricky part, is to say, well, just what is it that you're sending and receiving that you want to time it for? And that's always sort of the challenge. So it can be, that thing can be bits, it can be bytes, it can be packets. It really depends upon what you're talking about at the time of what it is. So for example, if you sent a packet, the latency might be from the time that you start sending the packet until the packet is completely received at the destination. Okay, so that would be one way. If it were a bit, it's when do you start receiving the bit, when you send the bit until it's received. What's the latency for that?
This the same concept that is being used to measure the internet speed, like speedtest.net?
Okay, so the question is this the same idea that's used in speedtest.net and like that when you measure your internet speed connection? So if I'm not, there's two components typically that they talk about. They talk about, they'll talk about your bandwidth, right?
It's upload speed and download speed.
Okay, upload and download speed. Yeah, okay, they call upload and download speed. That's the next set of slides. Okay, so this they usually refer to, well actually probably they do refer to it as latency, at least on some of the ones that I've seen. So that's what they're measuring here.
So in the ping example, it's a round trip, so not necessarily half, the latency would be maybe half-ish.
Yeah, so if you were looking, okay, so the question was, so when we saw when we did the pings, those are round trip times. So, I'm going to rephrase the question a little bit. So what's the latency, or what's the question what latency are we measuring in this case? So in that case, the latency measurement that we're collecting is the amount of time from when we start sending our request to have a ping until we've got an answer back. Okay, so that's more similar to a packet. Now, there's another latency that says, well, how long did it take to actually get to the other side? Right? And so we don't know. However, what we do know is that for the most part, the path that a packet takes to go and the path that it takes to come back is the same. That's not always the case, but we will make that assumption. And then we further make that assumption that, well, we don't know exactly how long it takes to get there or how long it takes to come back, but for a first order approximation, we'll say it's half that amount of time. So for example, if you were given a question that said the round trip time from A to B is X, what's the latency in sending from A to B? Right, so not the round trip. So I said I gave you the round trip time and I said what's the latency from A to B? The typical thing is you would take its X over 2. That's typically what you would, that's close enough for what we're working with.
You don't know for sure, though.
But you don't know for sure, no. It could be that, well, as we saw in those lists, right, we saw the most amount of time we saw was 12 milliseconds. The least amount of time we saw was 0.7 milliseconds. We saw an average of 1.6. So it could be, in fact, the case that we measure a round trip time of 2 milliseconds, of which one of them was 0.7 and the other one was 1.3 milliseconds. And so we don't know for sure. And just as a side note, that's why that's why collecting time on the internet is difficult, because you can't figure out what that latency is. Okay, so any questions about latency and sort of the points at which we measure these things? I should point out that the definition that I'm using here is sometimes different from other textbooks or things like that. Sometimes they will say it's from when you start to send until the first part arrives. Okay, and this one it's from when you start to send until the last part arrives. And the rationale for that with respect to networking is, and the stuff that we're interested in is, you can't do anything until the whole, for example, the whole bit, the whole byte, or the whole packet has arrived. So as far as you're concerned, you have to have it ready to go when the first bit goes out, but you can't do anything until everything that you need is actually shown up. So that's why we say, okay, that's the latency. It's from when you start to send it until you can actually do something with it. And that's why these things sort of measure, you do different things. You do different things with packets, you do different things with bits, you do different things with bytes. Hopefully, in a question or something like that, it's obvious which one is being talked about, whether we're talking about bits, bytes, or packets. It's usually fairly obvious. Okay, so any other questions about that? Okay, so the other thing that we observed was we saw this range of times that were there. I think if I do this right, so if we look at the times on the right-hand side, we'll see things like 12.4 milliseconds, 0.886 milliseconds, 0.9 milliseconds, 1.08 milliseconds. So there's this variation. And you should have observed the same sort of thing in anything that you did. You should have seen variation like that as well. And so that variation is referred to as jitter. Okay? So it's just the variation in the latency. So that's actually sort of how you talk about it. You say the variation in the latency is jitter. And there's actually not much more to say than that, then that's what it is, right? So, okay. So any questions about that then? Okay. So let's go back to this. So there's another piece of terminology. So why don't you give this a try too, and I'll do it at the same time. So one of the things that you can do is you can sort of say, okay, I want to send some amount of data. So the default amount, I think, is 69 bytes that it sends to the other side. But you can vary that, right? So you can go, for example, ping minus c, 10 minus s size, where size is how many bytes you want to send to the other side. So if you ask it to send, for example, 1,000 bytes, you'll send 1,000 bytes and you'll get 1,000 bytes back. Or maybe you'll get 1,054 or something like that. I'm not exactly sure how they count it. And so now the question the question will be, or is, so you do that, will that time change? Right? Think of how this works. Right? We take our data, we put it into a packet, right? And then we send that packet. The whole packet will show up. The whole packet will be turned around. So we're going to send a whole packet at a time. There is a maximum size to the packet, okay, so that you can have. So on Ethernet, for example, the maximum size packet you can have, I think, is 1,500 or 1,496 bytes or something like that. So it's below 1,000, but it's below 1,000. It's above 1,000, but below 4,000. Okay, so. Yep.
Sorry.
Oh, okay. So anyway, so I guess one question is, what would you expect to happen when you go from 1,000 to 4,000? So for example, would it take 4 times as long? Would it take just a little bit longer? For example, also for this time 1,000, since 1,000 will fit actually in an Ethernet packet that goes out on the network or out on the wireless and stuff like that, will that have any effect? Will the size have any effect on this? So if we try this, so we'll try well, that's not right. Oh, sorry, just I see. There. Oh, still not right.
UEC.ca or something.
Oh! We'll see if they will do this for us or not. So 1,008 bytes is 1.3, what does it say there? Yeah, 1.1 milliseconds. And if you look at my other one there, actually for 19 bytes or 69 bytes, it was 1.6 milliseconds. So in fact, this takes less time than before. That's maybe not intuitive. If we tried 1,200, so we have a big one there, right? 31 milliseconds, that was a big one. So a lot of jitter on this particular one, right? And so if we sort of throw the other ones away, we've got like the 1.38 and the 1.34, 1.37. So that's longer than the 1.13 ones that we're getting, but not longer than the most. If we go to 4,000, so at this particular point, it's given up on us, and it won't actually answer the question. It's just sort of saying, oh, that's it. So, oh, sorry, it got 1 through. Okay. Oh, no, got none through. Okay. So we could probably, I think if we go to 2,000, it'll do the same thing. See if CS is friendlier. So CS will do it. So in this particular case, since we're sending 2,000 bytes, I'm going to do 1,000 first of all. So if this reminds you a little bit about traceroute, well, it's kind of similar to traceroute, okay? Except what we're not doing is we're not setting the time to live. But so this time here, you'll notice that 0.6 seconds, 0.5 seconds. So when we did the other one, right, we got something like 1.3 milliseconds or 1.13 milliseconds to get to the other server. This one we got 6 milliseconds. So the latency to this server is less than the latency to the other server. So now if we sort of go back to this sort of picture, right, so what we sort of think about that, we've got all of these things interconnected. So each one of these pictures, each one of those components that we have to pass through to get from our machine to www.cs.ubc.ca versus ubc.wwubc.ca introduces some sort of delay or latency, additional latency as we go through it, right? And as we get further away. So one thing is that you can sort of determine from this is that if you have the same amount of data that you're sending and you're going to different locations, that roughly speaking, that if it takes longer as far as time is concerned, it's probably further away. Unless there's something that assumes that all of these other pieces of technology are roughly the same. If they're not, all bets are off, but that sort of is roughly the same. And we can assume that that's reasonable for UBC. So you'll notice here that we send 1,000 bytes. I'm going to try 4,000 to see if CS will do 4,000 for us. So it goes up by a little bit. So we go from 0.597 to 0.678. So it's taking longer, and if we did larger packets, it would take longer and longer and so, but it doesn't sort of go up necessarily linearly, right? So in the case of 1,000, when we did 1,000 bytes, it took 0.597 milliseconds. When we did 4,000 bytes, it didn't take 4 times that amount of time. Right? It took less than that. Okay? And so one of the things that we can do is we can say, well, how much data am I moving between my site and that other site? So we can say, well, I moved 4,000 bytes. Well, 8,000 bytes actually, because you sent 4,000 there, 4,000 back. So depending upon what you're wanting to calculate, but if you just sort of said, well, how many bits per second am I moving, or bytes per second am I moving? You could say, well, divided in half, because you're only interested in going one way. You can say, okay, well, in 3.35 milliseconds or something like that, roughly around that, I moved 4,000 bytes to the other side. So you could take 4,000 bytes, divide it by 3.3, and you get a number. And that number is how many bits per second or bytes per second, depending upon what units you're using, did you actually send. Okay? And so now now we have another metric that we can use. Okay, it's called throughput. Okay, so that's the amount of data that we can move from one location to another in a given amount of time. Okay. And so you'll see in this, we usually express that as bytes per second or gigabytes per second or gigabits per second or something like that. Now you had a question?
Yeah, so the increase in packet size does or does not slow it down?
Sorry?
The increase in packet size does or does not slow it down? Sorry.
No, it typically slows it down, yeah. So, but not by, so.
Not linear.
Not linearly, yeah. That's the thing. It doesn't slow it down linearly. So we'll talk about not next class, but on Wednesday we'll talk about, well, why isn't it linearly slowed down?
Also, if we just specify the number of bytes, it's just filled with zeros or something?
Yeah, I don't know if it's filled with zero, some random pattern or something like that. Yeah. So we've actually have a number of different things that there can be with respect to throughput. So we have something that's called bandwidth, and that's the maximum rate at which data can be sent over a link. So for example, that might be 10 gigabits per second. Throughput is the rate that you actually achieved. Okay, so that would be, when we did that with the wireless one, we would say, okay, well, I send 1,000 bytes per second, or not 1,000 bytes per second, I send 1,000 bytes in a packet. I can compute what my throughput was. I change it to 4,000, and I can get another throughput value. And then if I knew what the technology was, I could actually say, well, what's the bandwidth, which would tell me what the maximum is that I could have gotten. Okay, so if we had 10 megabits per second, for example, it'd say the most I could get is 10 megabits. When I send 1,000 bytes at a time, let's say I get 100K. When I send 4,000 bytes at a time, I get 500K or 600K a second. Okay? And then good put is the rate at which useful data arrives. Okay, so we'll go over these a little more in the next class then. Okay.